we go. Happy Wednesday, everybody. Welcome to today's AP Physics 1 Cram session. Today will be the first of 2 days that we're going to be doing rotational motion. Today, my rough plan is to do rotational acceleration, velocity, distance, that sort of stuff like that, and some torque stuff. And then next week, do the energy and angular momentum portion. So hopefully we can cover everything in some great detail by doing it that way. And if not, we'll adjust accordingly here. All right. Yeah, it's Wednesday. You guys are in the right spot. So good job being here. Upcoming stuff. This is Cram number 7, I think. Which means we have 3 more after this. Next Monday is rotational part 2. Then we do FRQ practice on the 6th. Basically, any FRQ practice questions, any topics. We'll talk about putting them together, finding the corresponding parts, where the points are hiding in those questions, and then just probably go through a bunch of practice with that. And then on the 13th, which will be 2 weeks from today, the day before your exam, is open Q&A. It's a super long stream. I think we're starting at like 4 o'clock Eastern and going till 9 o'clock. Don't quote me on that. I'm going to get more details on that by the end of the week. But that is there, and that will be just an open drop-in. We'll have a bunch of different streamers going through how to ace that 2-question AP exam. Okay. Speaking of this, yeah, the 14th, 4 p.m. for you guys. I do want to point out to you guys that the AP considers this exam to be open notes. So it is perfectly fine to write out a cheat sheet. And I'm definitely going to mention a couple equations today that you should write down on there that aren't on your reference table, but are super useful to have when it comes time to do these sort of questions. Okay, so let's, whoa, that's not the right slide. We're not doing simple harmonic motion. We're doing rotation. There we go. Rotational motion, stuff like that. So this is kind of the bird's eye view of what we're covering today, or hope to. Let me get my face out of the way here so you can see the whole thing. There we go. So we're going to cover basically what is alpha, what is omega, what is theta, how do those relate to V, A, X, that sort of stuff like that. How do we derive and come up with the equations of motion, and how are they related to the linear ones that we've spent pretty much the entire year doing. We'll get into torque a little bit, talk about why torque is so important, how we know if we have torque or not, or stuff like that. If at any time you guys have questions on there about any of these things, please leave a comment in the chat, and I will do my best to answer that as quickly as possible on there. Okay. So I think we're going to get started here. Before the stream, I threw out the question, are there any topics you guys want to cover first? And Jeffrey brought up translational equilibrium. So let's do a question on equilibrium and what it means, how it works, and stuff like that. This one's not in the slides, so I will add this one in momentarily. But actually, I'll do it right now because that sounds like a good idea. Duplicate, get rid of that. Okay, so this is the question I'm going to deal with first. It's a really old APC question, so it's not exactly a perfect fit for AP1, but it should be good enough in there. All right, and now let me switch over to my scratch pad, and we'll dive into this question. Okay, close that. Good, good, good. Paste that question in there. Paste. There we go. Okay, so first off, when we say translational equilibrium, or actually equilibrium in general, we are really talking about 2 very important things. Okay, so when we say the word equilibrium of any kind, we mean that the sum of the forces on the object is 0, and the sum of the torques on the object is 0. So up and down, left and right forces are balanced, Newton's second law, or first law, in there, as well as all the torque. So we're not going to accelerate in any direction. We're also not going to rotate in any direction. That is what we mean by equilibria. And this is what we're dealing with in this question. Okay, we know it's in equilibrium because this rod is supported. It's held in place. It's not falling around, falling anywhere. It's just sitting right there doing its own thing. Okay, that is the definition of equilibrium. All the forces are balanced and all the torques are balanced as well. So let's go through and talk about how we're going to solve this question and kind of get to our definitions of torque and stuff like that in there as well. So looking at this, we're going to start off by saying, okay, what are the forces acting on our object? So in this case, we've got, well, let's see, how many common forces are we talking about here? Let's draw some free body diagram stuff. So what forces are acting on this system? G, yep, okay, so I have gravity. Now here's the question, Jeff says normal, yep, that would work too. Okay, where does gravity act on this beam? Okay, the force of gravity always acts at the center of mass, yes. So in this case, RMG is acting right down the center of that object, center of mass. And anytime we're going to be asking you guys to draw one of these, we'll make it a bar or a circle, so it'll be pretty easy. You want to figure out where the center of mass is or anything like that. It's going to be in the center. Okay. We also have this thread. This thread provides a tension force. And as Jeff said, the axis also must provide some sort of, I'll call it a normal force going upwards as well. Okay, and these are the three forces that are acting on our beam. Okay, I know that the axis, the pivot point, okay, so why isn't there one? Let's do the math out to explain why there's not one, because I did kind of jump into that. We know both of these statements have to be true. We have to have equal forces and we have to have equal torques. Okay, let's start with Newton's force one. So this means that the force from the axis, I'll call it FA for right now, must equal out the weight when I add the tension. So the tension plus the weight must equal the force, the force of the axis plus the tension must equal the weight. Even if this becomes zero eventually, this equation is still valid on there. So this is sum of forces. Then we also have to look at torques. And for torques, we know that torque is the force times a radius, and they are perpendicular to each other. Now, out of these two options, if this is my pivot, this is R equals 0, hanging out at the axis, that means that the force from the axis cannot make a torque. It has zero distance from the pivot. Its radius is 0. So whatever number it is times 0 makes that 0. So what we can say here is the torque from the tension must be equal to the torque from gravity. Okay, gravity is going to want to make this rotate in a clockwise direction, and the tension is going to want to make it try to rotate in a counterclockwise direction. Those are opposed to each other. They can cancel each other out, which is good because we want to make sure our torques, total torques equals 0 here. So this will be T times L, the entire length of the beam, must be equal to mg times L over 2. Now, why L over 2? Because the weight acts in the center of the object. And if the entire beam is length L, that means that our radius to go from the center of mass to the other end is L over 2. We can do a little crossing out stuff. The L's can drop out. And we get that the tension must be equal to half of the weight of the beam. Well, wait a minute then. If the tension is half the weight of the beam, that means that my force from the axis cannot be 0. It's got to be some other number. In fact, it's got to be half the weight as well. So we can turn this into the force from the axis must equal mg over 2 as well, which means it's got to be pointing upwards, and there has to be that force there. So force mg over 2 pointing upwards and has to be there so the forces balance, because if we just looked at the torques, the forces wouldn't balance overall. Does that make sense? Okay. And that is the reason why part A asked us to determine how much of the force there was on the rod by the axis. So in this case, it's mg over 2, and it's pointing straight up. It's not pointing sideways at all because there are no other forces that it needs to cancel out. Okay, give you guys an example. If the tension in the string, if this was my beam, that's a terrible beam. If this was the beam, there we go, better. And the tension was going like this, then you'd have to have the force from the pivot be going up and to the right. Up to help balance the weight, and to the right to cancel out the leftward part of that tension. But that's not the case here. We are just looking at going straight up. So in this case, there's part A. Okay, get rid of that. All right, on to part B. Part B says, if the breaking strength of the thread is 2 mg, determine the maximum distance r measured from the hinge axis that I could put a box of mass 4m without breaking the thread. Okay. So now we want to put a box somewhere hanging on this beam. And we're going to measure from the hinge axis away, and we don't want to break the thread. Okay. Well, this again is more torque stuff. We can say we still want all the torques on this beam to cancel out. We don't want the thread to break and start rotating. Okay, a box, if we were to hang one on here, would make a torque, let's just draw that in, would make a torque going the same way as the weight of the beam, making the beam want to rotate clockwise. So what we can do is we can say the torque from the box plus the torque from the beam must be equal to the torque on the thread. Right? All the clockwise torques must be equal and cancel out the counterclockwise ones, so we are still balanced in there. So for the box, it's going to be 4 mg, that's the weight of the box, times, and I'll just call this r because I'm not sure what radius we're going to get yet. Then we can add in, what the heck did I touch there? Oh, I touched the arrow key. That's not good. Plus the box. We already did the box. The box is mg L over 2. And that has to equal our torque from the thread. They tell us the maximum force here is 2 mg. So let's use that, and let's make this 2 mg L as the torque on the thread. All right, now we can simplify a little bit. Every single term has an mg in it, so we can drop those out. And we'll subtract this L over 2 over to the other side. So I'll get 4r equals 2L minus L over 2. So that is 3/2 L divided by 4. R must equal 3/8 of the length. And that is how far away from the pivot I can put this box without breaking the thread. If I go over that point, thread breaks, we're in trouble. All right. Questions on that? So when it said the strength of the thread, I'm assuming, because I didn't mention anything else, that the thread is still attached at the same point it was before. So it would be the whole length L of the board. It's 1 L away from the pivot. And that's where we put the MGL part there. The force of it was the 2 mg, and that was told to us in the question. But the L, I just assumed it was at the same spot because they didn't tell us we were moving where that thread was anywhere in that problem. Okay. Other questions? All right. Then on to question number 2. Here we go. This one's, you guys think about it for a while here. We have a wheel composed with 2 pulleys of different radii, A and B, that are attached to each other so they rotate together. Each pulley has a string wrapped around it with a weight as shown. The pulleys rotate about a horizontal axis at the center. And they tell us when we let these things go, it starts rotating counterclockwise, starts rotating in that general direction. I'm sorry, that's the acceleration. That's my alpha is counterclockwise. Can I zoom in a little bit? Let me see what I can do here. Can I make this bigger? How's that? That better? Okay, yep, no problem. All right, so yeah, we got this wheel. We're going around. They told us the angular acceleration is in a clockwise direction. So which way is this wheel going to be rotating? Clockwise, counterclockwise, or nothing? And then explain. All right. So this one may seem like it's a trick question. It's not. I'm not intentionally trying to trick you here with anything like that. Simply saying that we've got this going on. Yeah, it's going to go counterclockwise. That's the answer there. Counterclockwise. Now, why is it going to go counterclockwise? Reasoning time. You do this a couple different ways. Explanation number 1, you can use the right-hand rule. Which, if you don't know what that is, let me find a picture for you here. It will look something like this. There's my torque and stuff like that. So yeah, there we go. Copy link. Come into here. Paste the link. Paste the image. Copy the image. Away. Sorry, this is taking a bit longer than I want to paste the image. Okay, there we go. So right-hand rule. Basically, if you were to take your fingers, put them in the direction of the force and curl it, your thumb points in the direction of the radius or the torque in here. So because we know that the acceleration is coming out of the page, coming towards us, that would mean that the torque is also coming out of the page towards us because Newton's second law. And then our fingers would wrap around in a counterclockwise direction because of that. So right-hand rule is one possibility. There's also a way I would like better, and just to say that since the wheel like that. Oh, simply saying that, hey, we're going to be moving in that direction because that's the way we were accelerating and there's no direction otherwise to go in. Okay. Second part, net torque, clockwise, counterclockwise, or none. I think I already said this one. Just stop spoiling answers to questions as I read through them. So for this one, again, we must have that counterclockwise torque. How do we know? Pretty straightforward. Yeah, okay. So right-hand rule again. Let me, yeah, sure. Find a better picture or a video with it. It's tough. Actually, let me put the camera back on. That would make a whole lot of sense. Okay, so I'm going to minimize this for a second here. Bring me back. Come back video. There we go. Make me big. Okay, so here's the idea with right-hand rule. Number one, it's your right hand, not your left hand. Okay. The idea here is that if you put your thumb in the direction the torque is going, your fingers will curl in the direction of rotation. So in this case, we have our torque coming towards us, coming out of the page. Okay. And that means that if I curl my fingers, they're going to curl in a counterclockwise direction. So because they told us that the torque or that the acceleration is coming out of the page, we know the torque must be going in the same direction as the angular acceleration. So out of the page and then twist. And that gives you a counterclockwise rotation for that. That is the right-hand rule. If we did it the other way, if we're going into the page, then we'd have our fingers curl in a clockwise direction. So it's one way that you can figure out the direction of the torque and rotation based on body parts and stuff like that you've got to work with. That help a little bit? Hopefully. It's not something that we need to know for this exam. If this was APC, I'd say you've got to know it down pat. For this one, it's not that big of a deal, but it is a nice, easy way of talking about how we know directions and stuff like that on there. Okay, so yeah, the net torque must be in the same direction as the... Yeah, what's up, Jeff? Yep, if I use the right-hand rule as my reasoning, do I have to go in depth? I would say that if I am the one grading this question, if this was the actual AP exam and stuff like that, and you tell me that the wheel is going to rotate counterclockwise because of the right-hand rule, I would give you credit for it. None of this part says you have to justify or go back to first principles or anything like that. So you should be okay just saying it's the right-hand rule. That's my reasoning for it. And you used it properly in this case, and it would be fine. If you did something where the right-hand rule didn't exactly apply, then you'd have to go into in-depth and talk about why that one has to be right. But yeah, for this, just saying it's the right-hand rule or applying the right-hand rule shows that it will rotate in a counterclockwise direction. That'll work fine. Okay. And the last one. How do the weights of these two things compare? I'm going to move this up a little bit so we can try to get them on the same page here. Pardon me for a second. Just keep everything together. There we go. How do the two weights compare? And explain our reasoning. All right. Which left has more mass than right? How do you know? Yep, because great, sure. So let's start from there. Because the wheel is accelerating counterclockwise, there must be a bigger torque going counterclockwise. Since torque, I know it's not the right symbol, but it'll work. Force times radius. And the smaller wheel something like that. So yeah, what I accept is because it's accelerating counterclockwise. Yeah, that's a good reason right there. But just to point out that we probably should go a little bit deeper than just saying because it's rotating that way. We should probably talk about, well, because it's rotating that way, we need to have a bigger torque on the left, going to the left than going to the right. Torque is force times radius and stuff like that in there. So yeah, but nice job. Nice job. Okay, any other questions going on with this one? All right, what's next? Oh, okay. Let me zoom this one in too, because this is going to be small as well. Grab that, get bigger. All right, so we've got, in this case, a light string attached to this kind of weird sort of setup here. It's a pulley attached to a block, and then the other end of the string is wrapped around this spinny thing on there. Okay. This, by the way, I don't know if you guys have done an experiment like this. There are kits out there that will let you basically set this sort of apparatus up. The goal here is to talk about finding the moment of inertia, finding I for the giant spinny portion of it. The idea here is that you're going to apply a torque at the base, and then you can measure the angular acceleration of those big blocks, and then be able to figure out I based on that. So, and I think that's what we're going to do in this question too. So let's dive right in and see what we can do here. So light string, vertical 4M, blah, blah, blah. Pulley that doesn't really rotate that difficultly. Good. So we get to ignore the pulley as everything in here. That makes our lives a bit easier. Wrapped around a vertical pole, radius R, shown in the experiment above. Released from rest, the block falls down. The string unwinds. Okay. So this is going to go down, and then we're going to start rotating. It doesn't really matter which way we're rotating here. It doesn't tell us. So we'll just put an omega on there that we're going to start rotating. I'm assuming it's counterclockwise. It doesn't matter for this case. Yep. They tell us I, which is good. They tell us the lengths. They tell us the masses. They tell us the big mass, the radius. Okay, all the good stuff. All right, so let's dive into this part. If the downward acceleration is measured to be A, what's the tension in the string in terms of the acceleration of the falling block? All right, so they mention tension, they mention the falling block, stuff like that. This to me looks like a Newton's second law sort of problem. Now, why am I saying that? Because nowhere in part A did they mention anything other than the falling block, right? We know this falling block has 4 mg going down. It must have some sort of tension going up, and we're told that there's an acceleration on it of A, whatever that happens to be. So we can say, pretty straightforward, F equals ma. Okay. They tell us that the downward acceleration, that the block is accelerating downwards. So that would mean that 4 mg must be bigger than the tension. So 4 mg minus the tension must equal 4m, well, 4ma, not g. And the basic Newton's second law sort of situation. And now we're just supposed to determine the tension T. Okay, so T must equal add, subtract 4m times g minus a. And there we go. Question so far? Okay. All right, on to part B then. Part B says, determine the torque exerted on the rotating pole by the string in terms of the mass of the block and acceleration. So is there an external acceleration other than gravity on the block? No. No, they're not saying that there's something other than gravity. It's just simply saying that the acceleration of that falling block is A, whatever that works out to be. So it's falling down, accelerating at some rate. It's accelerating because of gravity and the tension opposing each other. So the difference in their forces gives us the acceleration. And that's basically what part A was talking about there. All right, part B wants to find the torque exerted on the rotating pole by the string. Okay, so part C here, or sorry, part B, we want to find the torque on there. So torque equals force times radius. Well, this is pretty straightforward. The torque on here, the force from that is the tension in the string, and the radius is just r. So the torque in this case must be 4m g minus a, the tension we found in part A, times the radius r. So far, so good. Would it be 1L? No, we're not looking at the apparatus up here. And for part B, all we're looking at is just what is the torque on this chunk right down here. It said the string on the rotating pole. So what we're doing is there's a force pulling on that that's going to make it rotate. That force is the tension. It makes a torque F times R. They told us the radius already was R, so we're just plugging it in. We're not looking at the blocks yet, and I don't think we're going to in this part of the question. But if we were going to, then yes, we'd have to worry about the radius of each block from the top there would be 1L. But in this case, we're just looking at where it attaches, and that attaches at a point R away from the center of rotation. Okay. Part C. This is kind of a preview of where we're going next week. I wasn't going to get a ton into energy questions, but this is a good tie-in right here. When the large block falls a distance d, How does the rotational kinetic energy of the apparatus compare with the value? Can we include R in part B? Yeah, we kind of have to. We're not really able to do much else. That's a good question, though. Can we do this without having R? Yeah, I think it's just a poor wording of the question, John. I think we have to leave R in. Where else can we go with this? Well, we can also set this equal to I alpha, and just to see if anything actually happens. But I don't think it's going to do anything better. No, I mean, nothing's even going to cancel out there. You're left with a bigger mess that you started with. Yeah, R is going to hang out in there. You'll add an L in. I think it's just a wording of the question that we kind of have to have R in there. But good catch, good catch. We should always be looking for those things, like as to what are we allowed to have in our answer, what are we not allowed to have in our answer. I think this question just says, it says terms of mass of the block and the acceleration, and I'll put and the radius in there because there we go. Just to make that the way it should be. You're right. Okay, next part. Block falls down at distance d. How does the rotational kinetic energy compare with the value 4 mgd? Check the appropriate space below and justify your answer. Okay, so this block now falls down a distance d. So if we're talking about potential energy, this would be mg or 4 mg d. That's the amount of potential energy it has lost. The question is, will the rotational kinetic energy, k rot, of this thing equal 4 mgd, or will it be more or less than? And then we can talk about why. Okay, so John says it would be equal because all the potential energy is being converted to rotational kinetic energy. That sounds pretty good. We are definitely taking and talking about conservation of energy here, right? So all the energy beforehand must equal all the energy afterwards. We started with just potential energy. So that's the 4 mgd. And we are definitely turning some of it into rotational kinetic energy. The question is, do we have any other energies left over that is not rotational, that is not caused by the spinning of the two masses and poles, sort of stuff like that? And the short answer is internal is a possibility, but I'm going to ignore that. They don't mention anywhere in the question about friction or anything like that. So I'm going to ignore that. So Jeff, if you say it's less and our reason would be air resistance, would you still get points? I believe not. The reference tables, and you guys can go look at this at a later time. One of the conditions on the reference table says basically we ignore air resistance unless the question says not to. So in real world, absolutely we have air resistance. In magical physics land for this question, we don't. But it will be less. It definitely will be less than that. Okay? Because there is another kind of energy hanging around here. And it's not internal, because we're not talking about friction or air resistance and stuff like that. Yes, there it is, John. The block itself has kinetic energy. Okay, so because the block itself is moving downwards and has kinetic energy, we will not have this 100% conversion between potential energy and rotational kinetic energy. Instead, we can say, hey, this block also has kinetic energy. I mean the 4m block. The falling block also gains kinetic energy too. If the block were moving at constant velocity, would it be equal, right? So if we were to start this with the block moving at a constant velocity and ended at that same constant velocity, yes, then that would be equal, because then the block would not gain or lose any kinetic energy, and you'd have it all perfectly go over to rotational. But in this case, because the block is accelerating downwards, it's definitely going to be gaining kinetic energy as we go. All right, questions on that part? So our system is the apparatus block system. Yeah, that's fair to say. They definitely, and you kind of have to do that because in part C, they mention the large block. So that's the block part. And then they're talking about the energy of the apparatus. So they kind of have to include both parts there. Otherwise, you won't have a distance D to go with. And actually, a better way to put it, John, is our system is the apparatus block Earth system, so that we can actually talk about potential energy in there. So we'll have all three parts there. The apparatus, so we can talk about rotational, the block, so we can have potential, or the block and the Earth, so we can have potential, and then the block, so we can have kinetic as well. So all three parts, the apparatus, block, and Earth, would all be our system when we're talking about this energy in there. Okay, was there a part 2 to this? There was a part 2. Okay, let me expand this part, and we'll go to part 2. Whoa, there's 2 parts here. That's right, I just copied the whole thing. That's what I did. Big stuff. Okay. So now we're doing stuff in the general sense. We're going to do this experiment again, but now have a heavier pulley. So now we're going to have this pulley right here be more massive. So we can't just ignore it. Okay, everything else is the same. Would we predict our answers to be different? Yes, no, or why? Yeah, and it's going to be yes. Yes, I would expect that to be different. Otherwise, why are we asking this question? This massive pulley will then take some force to accelerate. You'll have to do some more Newton's law stuff with that pulley. But basically what it would be is now the tension in the string, this T1, is not the same as the tension that reaches the apparatus on there. They will be different in there. And we would have to go through and figure it out. But the gist would be that you would expect A to be smaller. If A is smaller, that means the torque is smaller. If the torque is smaller, that means the angular acceleration is smaller. And if that's smaller, you're going to have omega be smaller as well. So in part E, omega and final kinetic energy are going to be the smaller as well. So you're going to have a bunch of different things that are smaller. So the angular velocity is smaller. The linear velocity will be smaller. The idea here is that you have more energy caught up in rotational terms because I increased. So I went up, therefore omega goes down as a result of that. And if omega goes down, that means V goes down as well. So everything's smaller. Everything is smaller in this case than in the previous case because you took all the rotational energy that was just going to the apparatus, and now you split it between the apparatus and this pulley. The total amount of energy would be the same. Okay, if we're talking about the potential turns into kinetic sort of scenario from the previous part, the total, that 4 mgd, would be the same. How it splits up would completely depend on what the I value of this guy is. The bigger the I value for that pulley is, the harder it is to rotate, the more energy you're going to get caught up in there, and the less energy you're going to get transferred to the apparatus. And then vice versa. If this was a fairly easy to rotate pulley, you'd have more of the energy get transferred to the apparatus and less of it get caught up in rotational in the pulley. So Meg, this is a modified question. They included it because in the next part, which we're not going to get into because it's an APC question that is more advanced that we need to care about. They actually pivoted the blocks here and started saying, well, now what if we put them on chains so they can swing around and swing up and stuff like that, and talk about what happens to the energy there and what's the angle there and do the math with it. So the picture itself was from an old question that we kind of modified to make it work with AP1. And that's why it was there. It was just part of the diagram to make it easier. Okay, so John says, but would omega have to decrease significantly less than rotational inertia increases because omega squared? Yes. Short answer. The other possibility is to end up with multiple omegas, and I don't think that's going to happen, but you could end up with an omega for the pulley and omega for the apparatus being different and stuff like that. But in general, yeah, omega is smaller as a result of this. And it would be significant, assuming that your energy is the same in there. So yeah, you definitely end up with a much smaller omega as a result of that. Okay, so that question, we're going to check that off and move on. What do I got next? Do I like this one? I don't feel like doing math. I still feel I don't like doing math. Let's find something else. How about this one? This one's graphing. I like graphing. This is actually the most recent, the 2019 AP exam. This was their angular motion question on here. So this one involves graphs and stuff like that, which is why I think it's wonderful that we're going to review this one. I'm not expecting you guys to have to calculate a ton of stuff. You get a calculator, it's great to use and have there, but I'm going to expect a lot more derive and explain sort of stuff than I am crunch the numbers, which is why I skipped over that previous question. That was really just crunch the numbers sort of stuff. So let's knock this one out, and this will probably take us till the end of our time, and then we'll pick it up again on Monday with the next part of these. Okay, so this one was a 25-minute question. We're gonna try to cram it into about 15 minutes. So we'll see how good we get here. So disk is spinning about an axle at its center. A student's experiment reveal that while the disk is spinning, there is friction between the axle and the disk that exerts a constant torque on the disk, and it's the torque because of friction. All right, so what does friction do? Yep, it opposes the motion. It tries to slow things down. It tries to bring stuff to a stop, which means this constant torque we have going on here is going to constantly try to slow down the motion of this object. So we're going to start, and they tell us it comes to rest at T1. So we'll start at omega, and we'll come down to T1. Okay. It's a constant slope because we have a constant torque. Okay, and in fact, we'll end up with a constant acceleration as well. Let's make that constant. There you go. Almost close enough. Close enough. Constant negative acceleration. All right. So there's our graphs right there. Does frictional torque increase for an object spinning faster? Well, not really. Friction in its most basic, again, remember we going back, FF less than or equal to mu Fn. And we're always going to have static friction going on here. So really we can say it's equal to mu SFN on there, but it depends on the normal force. Nowhere in there is it talking about speed and stuff like that. Will it exert a torque better on an object that spins faster? I think it's going to be a constant thing. I think you're going to see the effect happen quicker because you're to see your omega drop off quicker. But the idea that the force of friction will change because of it, really shouldn't make a difference. Do that. All right, so there's our first part, graphs, basic kinematic stuff. Everything that we've learned about for September, October timeframes, acceleration, velocity, time, displacement, forces, stuff like that. All this stuff still applies to rotation. All we're doing is changing the symbols, but the underlying physics behind it, the idea that the slope of a velocity graph is the acceleration, that doesn't change. That's always going to hang with us and still be there. Okay, part B. Let's see, can I zoom in a little bit on this? I don't know if I can zoom in much. Let's see. I can move this up. I can make this bigger. There we go. That's bigger. So in this case, that's going to look terrible, but it'll work. You guys can read it. So they tell us the magnitude of the frictional torque exerted on the disk is T naught. Derive an expression for the rotational inertia of the disk in terms of T naught, omega naught, T1, and physical constants as appropriate. All right, so they mentioned torque, and I want to find I. So there's really only two possible equations that can work with that. There is sum of torques equals I alpha, Newton's second law. Or we can do delta L equals torque delta T, where L equals I times omega. So either way we want to look at it, angular momentum, which we'll get to next week. I'll solve it this way too, just so you can see it. But we're going to focus on that next week, or forces and torques. Okay. If we're looking at this, the torque must be equal to I. And now acceleration. Acceleration is nothing more than the change in omega over T. Right? Basic definitions. Acceleration is the change in velocity over time. So this means that my torque must be equal to I times 0. Actually, I'm going to ignore the negative sign here because we're just looking for magnitude. So this will be omega naught over T1. So my I must be equal to the torque times T1 over omega naught. And there is my answer. If I'm doing it the other way, then it would be I change in omega equals torque times change in time, I omega naught, torque, T1, why am I making the TI, T1, and then finally I will equal the torque, T1, over omega naught. Same exact answer. Just depends on what you want to think of it as, forces or an angular momentum. Personally, I jump to forces because that is the easier way for me to think about it. That's the one that my brain jumps to down there. Okay, part C. In another experiment, the disk again has the same angular velocity omega naught, but at this time t equals 1/2, we end up with oil dripping on the pan. Oil dripping on the pan, which reduces the friction. So we have our friction being decreased as we go through this setup. Okay. What does that do to our graphs? Yeah, it definitely will decrease the acceleration going on here, right? We shouldn't have as much acceleration going on. It's not constant anymore, so we get a curve. There we go. Okay, so we got both parts there. It'll be less acceleration, and it's not constant, so we're getting a curve. Now, what's going to be the same is we don't have the oil dripping until we hit t equals 1/2. So we should have basically, for the first chunk of time, before we hit t equals 1/2, there is no difference between this graph and the graph we did up at the beginning. They will be same exact thing. Because we haven't added any oil, we aren't going to change that. From t equals, or 1/2 t1, now suddenly we get a change in a curve. Turn off my ruler. Now we get a curve, and we'll curve down. Okay. Something like this. And also, because our acceleration is less, this is not 0 anymore, right? We don't actually stop anymore. All right, so this part, constant linear. This part, concave up. So can we assume it becomes frictionless? Who knows? You could probably make that case on there. It's going to depend on what you do with your graph. Like in this case, if I had it bottom out completely and go to a point where it kept the same velocity, then sure, basically we're frictionless, we have no acceleration. In this case, though, I didn't go that far. So I said we had some constant negative acceleration, and then we came up closer to 0, but we're not there yet. Okay? If you did have your velocity graph plateau out and go constant horizontal, then you'd have to get your acceleration up to 0 and then have 0 be that whole way. So let me see if I can do that in a different color on there. Yeah, John, so omega doesn't reach 0 because we don't have the same acceleration. It'll take longer on there. So let's just do a more extreme case. If I have this plateau off, something like that, then I would expect this to go up to 0 and then over. So it really depends. The question doesn't tell us a ton about how quickly this happens. So either one of those is perfectly fine. Okay. Yeah, either one's fine for that. Okay. Any other questions on this part? So we can assume there's a linear relationship between the amount of oil and the acceleration. Well, we know for a fact that the acceleration alpha is equal, or I alpha is dependent on the torque. The torque is the force of friction times the radius. The radius is constant. The force of friction, all we know is that this is decreasing. And I think it's safe to assume that it's linear. Can that segment be linear curved? The acceleration one, Jeff, let me read it to you off the AP scoring guidelines so you can say exactly what you're looking for here. For this graph, you get a curve with a clear change of slope at t equals 1/2 and decreasing speed thereafter. So having a change in what your graph is doing at that point. Slowing at a decreasing rate, so concave up curve between t1/2 and t1, and that it does not hit 0. That gets you 3 points. The second part for the angular acceleration graph, they want to say it has a decreasing magnitude between t1/2 and t1. So as long as this section right here is less negative, they're not going to be picky about whether it is curved or whether it is linear, because they don't give you enough information in the question to make that claim one way or the other. All they will be able to do is say there. Sure, definitely, especially if you make a mistake, kind of like I did, where I didn't accentuate that enough, that part on there, you can definitely leave notes to the rater that says, hey, this part should be constant and linear, and this part should be a concave up curve. It may not look like it, but that's what I'm intending to make it. That's perfectly fine. Perfectly fine. Okay. And then our last part. All right, so the last chunk, this is part D. We're now going to try to mathematically model what's going on here. So we're going to try to take this and say we have two possible equations that fit our data, 1 and 2. Okay, which one is the better choice for that? And why? Well, for a question like this, and this is a great qual-quant sort of thing here, we know what should happen with the torque, right? We know that the more friction or the less friction we have, the smaller the torque should be. So basically we're looking for more time leads to less torque. That's our general consensus for that. So which of those two equations, 1 or 2, is going to match up with that trend? That the bigger T gets, the smaller the torque gets. Yeah, it's equation 2. And why? Briefly explain. Okay, so here we go here. Let me try to type this up in a nice paragraph. Know from part C that torque decrease as the time increases. You could also put like indirect or inverse or something like that, but that's the gist of it. So, and there is your valid explanation. All right. Any other questions before we wrap up tonight then? That hour went pretty quick. All right. You're welcome, Meg. Can we find any of the rotational kinematic variables through graphs of angular velocity acceleration? Sure, Jeff. You can do the same exact stuff that you could do with a basic velocity time graph. So just a quick recap here. If I had velocity time, I know the slope will equal the acceleration. The area will be the displacement. For a rotational one, it's the same exact idea. This is omega and this is t. The slope is alpha. The area is theta. Same exact principle. So if you can do it with the graphs that you did in September, October, doing acceleration, velocity, distance graph, stuff like that, you do the same thing for rotational stuff. So the area of an acceleration time graph, if I were to do this, well, let's look. So if I had an acceleration time, the area here, whoa, wrong button. The area under here, stop clicking that, click this. So the area would be velocity. It would be the change in velocity. So the same deal with an alpha t graph, the area would be the change in omega. It wouldn't be the average because you're not looking at high-low. You're not simply just averaging 2 points on the graph. You're looking at the change in velocity there. Okay. The short answer would be anytime you have an equation like, oh, here's it, A equals delta V over T. If you solve it for that delta V, A times T, anytime you have your two axes multiplied together, you're looking at the area. So, yeah, there is that. So yes, all the kinematic stuff. Do I know any good resources for FRQs? Well, I know that pretty much every stream I do, I put in like 4 or 5 FRQs in there. If you're looking for other ones that are not In there, you can read the study guides on Fiveable. We'll have FRQs baked into them. You could look up the College Board stuff. If you've got access to AP Classroom, that's got a bunch of other ones that I can't publicly post on here because College Board is keeping those private. So you can have your teacher get you on AP Classroom, look at those practice questions and stuff like that in there. All that stuff are good options for more FRQs in there. Okay. Yeah. All right. You guys are welcome. And yeah, so Monday, we'll pick this up again. We'll do energy, angular momentum, and then we'll probably have a little bit of time at the end if you guys want to do some more of this stuff as well on there. If you guys could also shoot me an email sometime next week. It's peter@fiveable.me, just so I can start planning out the free response question stuff in 2 lessons from now, and just make sure that we're hitting topics you guys want to cover. So if there's other topics you definitely want to spend more time on, shoot me an email on those, and I'll make sure I put them in the next stream in there, or in 2 streams from now. All right, have a great night, guys. Thank you so much.